All right, I think we can get started. Thank you, everybody that's joined online, and good morning or good afternoon, depending on where you're located. We appreciate you joining us for this webinar. If you've been following along with our campaign, The Journey of Water, this is the first of two webinars that we'll be doing on this subject. There's been a number of blogs, and we're wrapping up. We're heading into the last third, I would say, of the campaign as we followed the evolution of water through all the various processes, whether they be treatment processes, its uses in industry and agriculture, and all the various things that we can do with water specifically. The focus of today's presentation is going to be very targeted on boiler applications and monitoring boiler water quality and the types of measurements we can do, why we do those measurements, and how they can help us in ensuring that we have optimal boiler water quality. A couple of housekeeping notes before we get started. Everybody is currently muted. It just helps us keep the flow of the presentation going well. We do, however, want you to feel free to ask questions. You can type them into the chat function within Zoho. You'll see that button along the bottom of the screen. And please note, you should have seen it already, but this webinar is being recorded, and the participants will get a copy of that recording afterwards. So let's get started. I'm going to break this up into three main topics. We'll talk a little bit first about what we call the steam water cycle itself, and how we use water, where it gets used in the purposes of generating steam, why we do it, how we use the steam itself. Talk a little bit about the types of parameters and the units within the steam system itself, and where and why we might want to do measurements at those points. We'll then look at sampling itself. These measurements are offline measurements. They're not done directly in the process for a number of reasons, temperature and pressure being the most obvious ones. So we extract the sample from the process, bring it to an analyzer. There's a lot that goes into doing that correctly and ensuring that we get a good measurement and a good result out of it. And then finally, we'll focus on the most common measurements that are done for boiler water applications. So let's get started and talk about the steam water cycle. And if at any point you're not hearing me correctly or anything like that, just raise your hand or throw a comment in the chat. I've got some colleagues that are monitoring the chat as well, and they'll let me know. So when we think about steam as a process fluid, its primary function is really to impart heat. The goal when we generate steam is either to heat up another process of some kind, or to use that steam, which has tremendous energy in its form, in its vapor state, to drive something such as a turbine or something of that nature. So what I'm showing here is more of the heating aspect of it here. We'll talk about power generation separately. But when we think about it as a heat generating fluid, we can see it as a closed loop system, basically. So we have a vessel that contains the water that we want to turn into steam, feed that water into a boiler where we use some kind of fuel to heat that water up to generate the steam. The steam is then transported throughout a facility via pipes or steam header of some kind, and then it will pass through heat exchangers, typically to add heat to a process or a vessel or something of that nature. You can even think in the Canadian climate, we often use it for the purposes of heat tracing for lines in plants that might be located outside, such as refineries. But what you see as well is that the steam is then captured, condensed, and then returned into the condensate receiver tank. So it's a closed loop system. The idea is that we want to maintain the quality of that steam throughout the process to ensure that we get the best operation of our process, but also that we also mitigate any extenuating circumstances such as safety concerns, damage to our equipment, etc. A variation on the theme, and maybe the most elaborate version of what we saw in the previous slide, would be a nuclear power plant. But when you zoom in on it a little bit, you see that the same process exists, and it's represented by these green lines here. Disregarding everything else that we see on the screen, the major components are still there. We have a condensate receiver tank, a pump that sends our liquid water to our boilers, in quotation marks, that generate the steam. The steam is then used to drive the turbines in this case, which generates the electricity, and then the whole process is repeated. The differing part here is that rather than using some kind of fossil fuel like natural gas to burn to generate the heat that we need, we're actually using another closed loop system with heavy water. The heavy water carries heat from the nuclear reactor to our steam generators and then circulates back down. So in this example that we see here, we have two circuits, but the function of the steam itself, or the process of the steam water cycle itself, doesn't differ from what we saw in the previous slide, and it still remains a closed loop system. Comment in the chat. My camera is off according to Gata, but let me turn that back on. It's showing as on my side. Hopefully everybody can see me. I'm just going to carry on. So when we talk about this, the water steam cycle, we really are talking about the chemistry that's involved. And you might think it's just water. What's the big deal? It is just water, but in order to ensure that we have the best possible conditions within the process, we want to make sure that the water is of the greatest possible purity and in certain conditions that mitigate some of the circumstances that I talked about earlier. Having the right balance, the right composition in the water's chemistry, gains us all of these specific points here. We improve efficiency, we lengthen component life, we improve plant economics, and we enhance personnel safety. You'll hear about different treatment processes that exist in the market. They all are effectively trying to accomplish the same thing in a different manner. But some of the more common ones that you might hear about are phosphate treatment, all volatile treatment, oxygenated treatment. Again, these are all different variations on a similar theme. The goal in each case is try to have the best water chemistry to mitigate or reduce all of these factors that we don't want to see in our process. So the chemistry is controlled for the purposes of minimizing things like corrosion, minimizing things such as deposits on surfaces, which can impact heat transfer efficiency. If the whole goal here is to transfer heat. So if we start building up a layer on our pipes or on our heat exchanger tubes or in our boiler walls, then we will require more energy to achieve steam generation, and we will transfer less energy from our steam to our process. So these are things we clearly want to avoid. Corrosion, for obvious reasons, is obviously a big problem. It leads potentially to damage to the equipment, but potentially also failures, which can be obviously bad for the CapEx or the capital equipment itself, but could be hazardous to personnel that are nearby as well. So these are all things that we want to keep an eye on or are trying to mitigate by controlling our steam cycle chemistry. The implications are profound. You can see some of the images here, what things can look like if we don't get it right. These are obviously things that have gone way too far beyond the control where we would like them to be, but the effects or the effects are obvious in these situations. We see here, for example, a tremendous amount of corrosion, even a hole in this line, a huge amount of buildup. You can't imagine that this tube is doing a very good job at heat transfer, corrosion and pitting on these turbine blades. I mean, these are all things that obviously are not going to lead to a good operation of our boiler. There are guidelines available from various organizations that talk about the types of measurements that can be done, where measurements should be done. how to take samples, all of these things. And I've listed them here as a reference. They all have slightly different takes on the processes, but you will see common themes that emerge. And as an example, I've pulled out from the IAPWS their key instrumentation requirements, and they basically go through all of the units that we saw in our original flow diagram: the condensate pump, the feed water inlet, the boiler drum downcomer, and they list the various analytical parameters that are recommended. An X is meant as you must do this, an O is meant as optional, depending on. So for example, degas conductivity is deemed optional at the condensate pump, but it's only if you have a fast cycle process. What do I mean by fast cycle process? I mean a plant, for example, that may be running at a lower setting and is asked to come up on demand, such as a peaking power plant or something of that nature. There's tremendous economic benefit in being able to start up the plant more quickly, and measuring degas conductivity can allow the operators to do that. Without a degas conductivity measurement, they're going to rely on the cation conductivity, which may take them longer to actually achieve their trigger point where they can actually start the plant. That's lost money for them. And then again, depending on what the unit looks like, whether or not an air-cooled condenser is used versus a water-cooled condenser, a sodium measurement may or may not be required. Obviously, if it's air-cooled, then we're not introducing potentially sodium via leaks in the condenser. But if we have a water-cooled condenser, then any kind of leak could introduce untreated water into our steam water system, and that we would see as an increase in the sodium value. So there's a list here. Again, it's here for reference. This is not an absolute. These are guidelines, but it's very useful to see these, and it carries on to the other units within the process. The one thing that you will see, or I hope you noticed, is that in almost every case, or perhaps every single case, conductivity is pretty much a must. Conductivity is the simplest and the most basic way of determining a water's purity, in quotation marks. It is effectively that. The purer the water is, the less conductive it becomes. And as we add impurities to the water, the conductivity will increase. There are different versions of conductivity, and I'll talk about those in more detail as we go through the presentation. So back again, a different view again, and I wanted to use different representations to show that they might look different, but when you drill down on them a little bit, you realize all the same components are there. But now we kind of look at it from the standpoint of, okay, on this process, where are the measurement points? And you see them all listed here. So, you know, monitoring the specific or cation conductivity on the makeup water, oxygen, dissolved oxygen on the deaerator, a bunch of different parameters on the boiler water, and so on and so on. So again, I'm not here to explain the reasons why those are there. We're going to talk about that in a little bit more, but in every single case, the goal is this is a potential point where it makes sense to do this measurement because of what's happening within that process. So for example, on the condensate, condensate tank, we're looking at things like sodium potentially if we have a on the condensate condenser, we're looking for sodium because if we have a water-cooled condenser, this is where we have the possibility of introducing a leak of untreated water. After the deaerator, of course, it makes sense to monitor for dissolved oxygen. If the deaerator is not doing its job, we will have excess oxygen in our water. So reasons why, the locations, and the recommendations as suggested by those various organizations that we looked at. Okay, so we understand the why now, and the types of measurements that we're going to be asked to do. Let's talk a little bit about the how now. And the how really starts with the sample system. It's true of anything that we do. And Novatech, if you're familiar with the company, is a company that makes sells analyzers, of course, but also designs and fabricates sample conditioning systems, sample extraction systems. And it doesn't matter whether we're talking about boiler water, whether we're talking about an emissions monitoring system on a stack, a process analysis, it really doesn't matter. If we have poor sampling techniques or we don't choose our sample point correctly, we're going to get poor results. You can have the best analyzer in the world. If you don't follow or pay attention to those first 2 points, the results are either meaningless or bad, because either we're monitoring from a point that is not representative of what we really want to see in the process, or we have potentially altered the composition of the sample that we're trying to measure, and the results are no longer meaningful. So just like we do with gas analysis applications, just like we do with any application, we really have to think of this as a complete system. And so when we talk about a SWAS, is the term you'll often hear, a steam water analytical system, it has to be all encompassing. It's not just the sample conditioning panel and the analyzer. It also has to include the sample extraction point, the sample transport, of course, the conditioning, of course, the analysis, and the signal generation. How are we going to relay that information back to the operators that are running this plant? So let's start from the start, if I can say that. The sample system itself. The purpose of the sample system is to bring the samples from the process to the analyzers so that we can measure the parameters that we need to measure, that we saw listed earlier in all those guidelines. The key is that the sample must be representative. It has to reflect what's actually happening in the process. And there are some best practices and some guidelines that are discussed within those guidelines that I talked about earlier from EPRI and IAPWS. But even just on basic good practice, we understand all these things. We can't alter the composition of the sample. If I'm using improper materials of construction, or if I'm not paying attention to the dew point of the sample, and I have multi-phase sample that I have to deal with, I'm altering the composition if I don't do my job correctly with the system. There are best practices that talk about where the sample point should be taken off. Okay, we say we want to measure the condenser, but where on the condenser? And there are things that we have to look at, such as avoiding dead legs in the system, not sampling from the bottom of a pipe or the top of a pipe, especially if it's multi-phase applications such as superheated steam, things of that nature, using the right type of probe. So an isokinetic sampling probe, for example, for applications where we have multi-phase measurements to be done. All of these things have to be taken into consideration. The way we transport the sample has to be part of it as well. We have to think about it from the standpoint of, again, not altering the sample itself, but bringing it to our analyzer in a timely manner. If it takes 3 hours to bring the sample from the probe to the analyzer, then the result I get from my analyzer is not what's happening right now, it's what happened 3 hours ago. So is that actually useful from a control perspective? So sample materials of construction obviously have to be of high quality so that they don't impart anything to the sample itself. And obviously we don't want things that are degrading and corroding and potentially leaking. But also things like the diameter of the line, ensuring that we have sufficient flow velocity in the line. It's not about volume so much as it is velocity, because we're trying to ensure that if we have, for example, a multi-phase sample, or if we have any kind of particulate in the line or anything of that nature, that they are swept along in the line and not accumulating potentially in a low point, or because my velocity is too low and I start to actually build up sediment in the bottom of my line. We would like to have the line always sloping downwards whenever possible, from the takeoff point, from the probe to the analyzers. And insulation, and this is an area that's a little bit counterintuitive to our Canadian customers, insulate only where necessary. We're going to be sampling from processes that could be at very elevated temperatures, and the analyzers are not going to be able to handle the water that we collect at those temperatures. So insulating is counterproductive for us. We only want to insulate where it's absolutely necessary. Insulate where there's a risk of cold temperatures that could freeze the sample. In fact, heat tracing would be required in a situation like that, or where maybe there's a risk of contact, where somebody could put their hand on the line and maybe get a burn, but otherwise do not insulate. Let the ambient air actually start to cool the sample for you and reduce the amount of work that has to be done at the sample conditioning system. Sample conditioning, well, as its name implies, prepares the sample. It conditions the sample. It's also where we do things like provide isolation so that we can do maintenance work and things of that nature. It's where we control the temperature. It's where we control the pressure, the flow. It's where we might filter the sample if necessary. And we also have to think about giving access to grab samples. So if a technician or an operator needs to bring a sample back to the laboratory to validate the performance of an analyzer, that would be where that sample would be accessed. Typically, what you'll see for sample conditioning systems for SWAS panels will be everything mounted on a single plate. And it would be installed adjacent to the analyzer or analyzers, depending on how many parameters have to be measured for that specific point. Sometimes, if the plant is compact enough, all of the SWAS panels will be in a single room potentially. If it's a little bit more spread out, you might have multiple SWAS panels throughout the facility. One SWAS panel here that does the condenser, another SWAS panel over there that handles the deaerator, whatever it might be. So temperature control is relatively straightforward. The reasons are obvious. We have to condition the sample to a temperature that is suitable for the instrument or instruments that we're going to be feeding with it. If our instruments are only suitable for up to 70 degrees C and I'm bringing a sample in at 150 degrees C, that's clearly not going to work. We also have to think about safety. And the guidelines or the general rule of thumb is that we're targeting a temperature below 50 degrees C. It's relatively achievable to get down to those types of temperatures without using a tremendous amount of cooling water. And it's a temperature that is typically amenable to both the instruments that we're going to be using and is safe for operators. So if you get 50 degrees C water on your hands, it will be hot, but you're not likely to cause a burn necessarily. So that's kind of, again, a rule of thumb. It's not an absolute must, but that is typically what we use when we're trying to size the heat exchangers. I use the word heat exchanger and cooler interchangeably. They do the same thing. The sizing of the cooler is critical to ensure that we do it right. And the parameters that we have to understand are these four. Any change in these has an impact on our ability to remove heat from the sample. So obviously the temperature that I'm bringing the sample in at, the flow rate that I need to achieve, and that will be a function of a few different things. If you think back, we want to ensure that we have a certain velocity in our transport line that has an impact on the flow rate, and how many instruments that we're going to be feeding with this specific cooler. If it's one instrument, we might only need 2 liters per minute or something like that. If it's 5 instruments, because we're measuring multiple parameters, obviously we're going to need more water. And then the flip side to that is the same parameters, but now on our cooling water side. If the cooling water has a relatively consistent temperature, that helps, of course. But if we're using cooling water from a source where the temperature may vary seasonally, for example, as it often does in Canada, we have to look at the worst case scenario. What's the highest temperature my cooling water may be at, and what's the highest temperature my sample may be at. And then we use those to size the cooler correctly and ensure that it's capable of achieving that target temperature of 49 degrees C or less. So all of that is the goal. But then as a safety check, what we often might do is put in a thermal shutoff valve. A thermal shutoff valve downstream of the cooler is there to prevent potential damage to the instruments if for some reason say the cooling water were to be shut off inadvertently, and now our sample temperature passes through without cooling and is heading towards our instruments at 100 degrees plus or something like that. Um, that's obviously a problem, but also for safety. We don't want to expose personnel potentially to temperatures beyond 50 degrees C. A thermal shutoff valve will automatically close or shut off the flow of the sample if the temperature exceeds its set point. We have to control flow, obviously, we talked about that, but also pressure. Boiler steam water systems operate at very high pressures. And obviously, those are not suitable for the analyzers that we're going to be sending them to, but also there's a safety factor involved here. The best practice in a system like this is to cool the sample first and then control the pressure. And why is that? Well, if my sample is coming in at 150 degrees C, as we talked about earlier, if I drop the pressure first, I'm going to start generating steam. So I'm going to have water boiling in my sample conditioning system, and that's not what I want. I want to keep it in the liquid state in my sample system. So the procedure is to cool it first, bring the temperature down, then control the flow and the temperature. And this is the typical setup that we see. So hot water coming in from our sample probe, going through our cooler, which has been cooled with a continuous supply of cooling water. Then I have my flow/pressure regulation valve, my optional thermal shutoff valve, and a back pressure regulator downstream of my takeoffs to the analyzers. By doing this, I ensure that I have consistent pressure going to the analyzers that are connected to this panel, and I don't have to have individual adjustments on each one. So I maintain back pressure on the sample conditioning panel, and then that gets sent to the individual analyzer panels that are adjacent to it. Obviously, in Canada, CRN is a big deal. And if for those that are familiar with Canadian registration numbers, they were born out of this specific industry. In Alberta, it's the Alberta Boiler Safety Association. This is the very type of application, very type of industry that APSA targeted when they came up with these standards and the requirements for Canadian registration numbers, which is a pressure certification, a pressure directive. So the systems are going to have to be CRN approved for installation in these jurisdictions. Okay, that's a very broad overview of the why, the how in terms of the sampling. And now we're going to talk about the types of measurements that we're going to be able to do, and the reasons why we do these measurements as well. A little bit in terms of why they were specified by those various organizations, EPRI, VGBE, IEPWS. Why do they ask for a pH measurement here? Why do they ask for conductivity? We'll talk about that a little bit now. So why? The goal of this system is to have optimal water cycle or water steam chemistry. So the way to ensure that we have the optimal chemistry is to monitor it. And if we have optimal chemistry, we avoid all of these things or achieve all of these things. We prevent corrosion or at least minimize it. We avoid deposits. We reduce downtime due to equipment failure. We maintain efficiency, heat transfer efficiency. It's critical. That's the whole point. Energy is money. If you have to use more fuel to generate your steam, then that's costing you money. And of course, protection of personnel and equipment. So having optimal chemistry allows us to do that. The only way to ensure that we have optimal chemistry is to do these measurements on the quality of our water. So we'll start, and we're kind of going in order of complexity with these, but it also follows along that chart that we looked at originally from IEPWS. And the first column was pH. Why do we measure pH? Pretty much all of the water chemistry programs that I mentioned earlier, like all volatile treatment or oxygenated treatment, they all target to operate at an elevated pH level, typically between 10.5 and 12 pH. Why? They do that primarily to avoid these things. There's an optimal region where we minimize acid corrosion and we minimize scaling. And outside of that window, one or two of those things starts to take over. If we go too high, then scaling becomes a factor. If we drop down too low, then corrosion becomes a factor. So there's that window. There's a sweet spot of operation between 10.5 and 12 that we're always targeting with these types of water steam treatment processes. So by monitoring the pH, it's a check. We see that we're in the right region, that our treatment program is working the way it should, and that we're doing the best we can. When we're talking about clean water like we need for boiler applications, we have to keep in mind that we're dealing with water that has a very, very low ionic activity. So we have to think about that when we're selecting our pH electrodes, because not all pH electrodes are created equal. Some pH electrodes are really optimized for monitoring in and around natural water pH levels. So for wastewater applications or potable water applications. Others are really optimized for acidic environments. Others are optimized for these alkaline environments that we're talking about here. So choosing the right pH sensor with the right electrolyte formulation, with the right type of junction is critical to ensuring that it's going to work properly in this type of environment. Another thing which is very useful in this kind of application is digital sensing technology. And digital sensors don't do anything different in terms of the pH measurement itself. It's simply a matter of having a digital interface between the sensor and the transmitter, and that allows a tremendous amount of feedback and information that we could get in the past, but required significantly more effort to get. So it's live feedback on things like the sensor 0 point, the slope, its wear, its response time, and that really gives you comfort in terms of the quality of the measurement. So with these types of instruments, normally the only way to ensure that the instrument is working properly is to validate it with a known standard. So you perform a validation or perhaps even a calibration. But the comfort that comes with digital instruments is that you can see that between those checks and ensure that, yeah, the sensor's checking itself, it's looking good, it's happy, I feel confident that this number is correct. Moving on to dissolved oxygen, now we've got kind of a reverse, or well, it's similar in the sense that with the pH we had very low ionic activity. With oxygen, we are trying to remove as much oxygen as possible from our water. So we measure the dissolved oxygen. Any type of dissolved oxygen or increased dissolved oxygen levels lead to increased corrosion in our system, especially if there's any carbon steel or copper alloys or anything of that nature. Corrosion will lead to creation of oxides, ferric oxide, things of that nature, which leads to deposits. And those are all the types of things we want to avoid in our boiler due to heat transfer efficiency and plugging issues, flow issues. So the reasons are pretty obvious. Traditional and parametric or Clark style sensors will do the job. They can get down to the levels that we need. We're normally running in the region of 6 to 10 parts per billion if we're not using an oxygen scavenger. If we are using an oxygen scavenger, we're even below that. But the goal here is not necessarily to monitor the absolute value. It's to look for an unusual situation. Hey, normally I read 0 or 1, and I've jumped up to 10 all of a sudden. Something's happened. Maybe my pump seal is leaking, or maybe my deaerator isn't operating correctly. Those are the triggers to say I need to go investigate and see what's going on. Again, with dissolved oxygen, super useful to use digital technology. You get some of the very same benefits as you do with the pH sensors. And it's worth noting that, I talked about the fact that DO is a good indication of an issue potentially. If we're talking about applications where it's not steam for power generation, but steam for heating of processes, there are other parameters that we may want to look at as well. So imagine we're using steam in a heat exchanger in a refinery or a petrochemical plant. The risk of contamination now, or what we might see if there's a leak in a heat exchanger tube, would be things like hydrocarbons breaking through. So here's where an analysis such as a TOC measurement would allow us to see that we've got something coming through, we need to take action, our heat exchanger tubes are leaking, what are we going to do about it, and take corrective actions. They're not talked about in the standards from EPRI and all that. They're very much focused on power generation, but the reality is we generate steam for other purposes as well, and that's where those types of measurements may come in handy. Conductivity, let's spend a little bit of time on conductivity, because as I mentioned earlier, it is kind of the tell-all measurement when we're talking about water quality. And that's the reason why there's actually 3 different types of conductivity measurements that we can do. The definition of conductivity is the ability of a solution to carry an electric current, conductivity. And it really is that primary analytical measurement. The 3 types that we will see in this world are specific or total conductivity, which is just a straight conductivity measurement of the boiler water as is. The other term you will see is acid or cation conductivity and degassed acid conductivity. And I'll talk about those 2 separately in a minute here. It's important to know that conductivity rises as temperature rises. So obviously temperature compensation is a must. All of the conductivity sensors that are commercially available for this type of analysis incorporate a temperature sensing element as well. So that shouldn't be an issue. And I'm told my camera is off again. Let's trigger that. And well, hopefully that comes back. The other thing to see is that depending on what the contaminant is in the water, the conductivity curves or compensation curves differ as well. So understanding what we're looking for is useful in these types of applications as well. Okay, so the 3 measurements that we talked about a moment ago. Total conductivity, direct measurement of the water as is, untreated, no change. The next one, and probably the most popular that you will see in boiler water measurements, is acid or cation conductivity measurement. And in that case, what we're doing is we're passing the water sample through a cation exchange resin. And in that resin, we are removing some of the chemicals that are used in that dosing, in that water treatment process. They create an interference of what we really want to see, which is the conductivity from the rest of the process. So if we take out, for example, the NH4 plus from the amine dosing, we actually, or the oxygen scavengers that might be present in the sample, we get a clearer picture of the true nature of the water itself. So it's the most common measurement that it's done, and more often than not, what you will see is total and cation conductivity done together on the same instrument. So you'd have an instrument where you have the sample flowing through a flow chamber going to one conductivity sensor that does the total conductivity reading. From there, it flows through the resin and then onto the second sensor that takes a cation conductivity reading. So you get both measurements simultaneously at all times. The third one, and it's less common, and I touched on it earlier, is degassed conductivity. And degassed conductivity addresses the fact that even going through a cation conductivity membrane, we don't remove some of the components such as CO2, the acidic components will not be removed necessarily. And the way to remove them is to actually take our water nearly to the boiling point. So in a degassed conductivity measurement, we actually have what's called a reboiler over here, where we're taking our condensate that's been boiled already, and we're nearly reboiling it. We're taking it up to a point just before the boiling point. We don't want to generate steam, but we want to get pretty darn close. And by doing that, we remove as much of the CO2 as possible. It actually comes off as a gas. So then after doing that, we cool the sample back down. There's a heat exchanger, and we do a third measurement where we measure acid degassed conductivity. So those are the three possible measurements that can be done for conductivity. Again, the degas conductivity really only comes into play when we're looking at stuff like peaking plants, where we want to be able to start up our process as quickly as possible. And the trigger to start generating electricity is I got to go through my polishers and my cleanup until I get below this value. Till I get below that conductivity value, I can't start. I'm not setting my water. And by doing a degas conductivity measurement, we get there sooner because we see the true number. Degas conductivity will always be lower than cation conductivity, will always be lower than total conductivity. So you can see how measuring this number gets you there sooner because it's going to be the one that is really representative of the contaminant level in the water. We're normally looking at numbers in that 0.2 to maybe 32 microsiemens per centimeter in boiler water. So we are really looking at quite low waters, obviously levels, I should say, but obviously we may have a higher trigger point for blowdown. Again, that's very much process dependent. The sodium measurement is the one that really gives us eyes onto what's happening in terms of heat exchanger or particularly condenser breakthrough, condenser tube leaks, if we're using water as our cooling medium, so untreated water as our cooling medium. The slightest leak will allow sodium to leak in because it is the most water soluble component. So we're pulling it all the time from every possible location. So untreated water will contain significant amounts of sodium, and we'll see that very easily as we pull it into our process if there's any kind of leak. As you can see, these are significantly more elaborate measurements. We're getting into what I would call wet chemistry technology here. So these are ones that we approach with caution. It's like, do I need this? Do I really want to do this measurement? Maybe I'm happy just going with a grab sample and taking that to the laboratory. But if there's benefit in doing it online, there are ways of doing it and managing it quite effectively. You can see the impact of sodium. Sodium will lead to things like pitting, caustic gouging. If left unchecked, these things can be catastrophic. So it's not something to be taken lightly. It has to be looked at very closely. The way it's done is relatively simply in that we can source ion-specific electrodes, and in particular one that is specific to the sodium ion. However, it's still sensitive to hydrogen ions. So even though we have an electrode that is specific to sodium, it will respond to hydrogen. And unfortunately, its sensitivity to hydrogen is approximately 100 times greater than it is to sodium. So in order to do this measurement, we absolutely need to reduce our hydrogen ion content. And the way we do that is by increasing our pH, taking it as high as possible. And normally we're targeting something in excess of 11 pH. And we do that by dosing our sample with DIPA, or diisopropylamine. By doing that and monitoring the pH in our sample, so we measure the sodium, we monitor the pH to ensure that our DIPA addition has been happening correctly, we get a good representative value of the sodium content in the sample. And you can see the impact here. If the pH is 11, the offset due to the hydrogen ion presence is very low, but as we lower the pH, we get a huge offset from the actual reading because of the presence of the hydrogen ions. So it's super important to do it properly. We're typically looking at numbers less than 10 parts per billion, 2 to 6 ppb, depending on which type of treatment program you're using and what sample point we're looking at. So an effective measurement that's not that complex, but still all of a sudden we're looking at something that, well, it requires some kind of reagent addition and what have you. There's pumps and circulating pumps and things like that, valves. it is more complex. And so obviously customers will take this with some measure of consideration before choosing to embark on doing a sodium measurement potentially. And the next one, and the most challenging, is silica. Silica is, again, everywhere because it is the second most abundant element in the Earth's crust. So we find silicon dioxide, in water. It is highly soluble in steam, and that's bad because what happens is it will be picked up by the steam that we generate in the boiler. The steam travels to, in the case of power generation, to our turbine. At the turbine, it will deposit on the cooler turbine blades and form a layer of silica on the turbine blades. And that can be very bad. And this, my camera just keeps turning on and off. I have no idea why. There we go. We'll try again. So the turbine will get deposits on the turbine blades, which obviously has an impact on the efficiency of the turbines, but also could lead to potentially creating imbalances in the turbine itself. So you can well imagine a turbine that's spinning at hundreds of thousands of RPM. You can't afford to have that even a little bit off balance. So if we start forming deposits on the turbine blades, that can be very, very dangerous. So I'll go back one slide because I jumped ahead. Yes, so exactly what we talked about. 0.1 millimeter deposit can reduce thermal transfer by 5%. So it does not take a lot of a layer of silica on the surfaces to start impacting thermal transfer efficiency as well. How is this measurement done? Well, this is the most complex measurement that you'll see. It really is a series of reagent additions, stirring, waiting, adding the next reagent. It's a little chemistry lab in a box. So the analyzer is fully automated, of course. It will do all of the reagent addition and timing and stirring and what have you. And at the end of the cycle, when it's added the last reagent, stirred it, given it enough time, it's a photometric reading. So we're looking at absorption at a specific wavelength, and that absorption is specific to the silicon dioxide content that we started with in our water. So again, more complex, more stuff to think about, reagents to keep replenished and ensure that you don't run out or anything like that. But it is possible. It's certainly doable, and it's commonly done in this type of industry. So that's pretty much my presentation. If I can sum it up in a few words, proper SWAS system gives you the information that we need for our water steam chemistry in our boilers. And I refer you once again to the various guidance documents that are available from organizations such as EPRI, VGBE, and IEPWS. If you don't already have that information on hand, it's super useful to look at those guides and see if there are other parameters that you could be monitoring that could help you ensure a really good treatment strategy and know that the condition of your boiler water is at its peak and optimal. And finally, I'll finish with just a short plug. This is the world we live in. Novatech provides SWAS sampling and conditioning equipment and the analytical equipment that's required to do the measurements as well. So if you have any kind of application such as this, by all means, don't hesitate to reach out to me or your local Novatech salesperson. If you know who they are, you can reach us at info@novatech.ca as well. That is my presentation. We finished a couple of minutes early, which means we are, or I am, open for questions if anybody has them. I don't see.
Actually, there is one question in the chat. Yes.
Can silica go past the turbine and deposit on a heat exchanger? Absolutely. Because it's carried by the steam, some silica will continue on potentially past the turbine blades. And that's really the danger of it, is that it is carried by the steam itself and will go through all of the sections of the process that the steam touches. And once it reaches a cooler surface, you will create silica deposits, and that's where you also get the undesired effect of that reduction in thermal efficiency or heat transfer. Any other questions while we have a couple minutes here? If not, then I will wrap it up. I thank you all for your attention and your time today. Sorry about the camera issues. I never saw it go off here. My little light has been on the whole time, but it seems that the platform is playing tricks with me. But we will package this up for you, and GATA will ensure that all the participants have access to the recording of the presentation. Thanks very much, everyone. Have a good day.